Okay,
Okay.
pay attention to the problem. This is the rated voltage, the rated speed. Okay, yeah, I will have, this is my first speed. Okay, this is the rated rotor speed. Yeah, I will have the subsynchronous speed is this one. So I have two speeds. Okay, and besides, this is the equivalent resistance and this is the equivalent reactance. MPPT means the maximum power point tracking. Okay, continue, Mr. Lozada, please.
Mm. Letter B, the RMS stator and rotor currents. C, the stator and rotor winding losses. D, the stator and rotor active powers. E, the net power delivered to the grid and efficiency of the DFIG. And F, the fundamental grid current.
Okay, thank you. That is it. Okay, so pay attention to the data. This is the data for the double FET induction machine. I will have 5 megawatts. The frequency of operation in this case is 50 hertz. Okay, and these are the parameters. These are real parameters of the double FET induction generator. Okay, so the rated mechanical power is 5 megawatts. Okay, what I need is the rotor resistance. Okay, so pay attention to the rotor resistance. This is the rotor winding resistance. Is 1.446 milliohms. Okay, what I need is the frequency of operation. So let's clear this part. Okay, so first of all, the frequency of operation is the first data. The stator resistance, this is the stator winding resistance, is this value. So pay attention to the rated mechanical torque, okay? And besides, I need the rotor winding resistance, is this value. The stator leakage inductance, the rotor leakage inductance, but I don't need the leakage inductance. What I need is the leakage reactance, okay? So I need to compute. This is the stator leakage in reactance. Yeah, I need to compute the rotor leakage reactance. Okay, for that, by definition, is equal to the speed times the inductance. Okay, so I will have times this inductance. Okay, the same for the rotor, right? So I will have the speed times the leakage inductance. Okay. Yeah. What else? I need I need the number of pole pairs. Okay, this in this case is equal to 3. The rated sleep is this value. Okay, so the main thing is the rated, in this case is the rated rotor speed, is this value. Okay, so I will have two possibilities in order to compute. I will have two possibilities in order to compute the generator mechanical torque and power. Okay, because I have the data for the rated speed. Okay, the problem is asking me to compute the generator mechanical torque and power, but in this case for the second speed, let's call this speed 2. This is the subsynchronous speed. Okay, so I have two ways in order to compute the torque and the power. Okay, the first one is an approximation. Okay, so this is for the torque. This is a quadratic equation. Okay, and for the power is a cubic equation. Okay, so if I know this value, for instance, the ray value, the same for the, let's say this is the rated mechanical torque. Okay, and this is the rated mechanical power. Okay, so my first way in order to compute the mechanical power is an estimation. Okay, so for that I will use the ratio of the speed. Okay, I will use the ratio of the speed. It means I need to compute the ratio of this is let's call this speed number, speed 2 over the speed 1. The speed 1 is the rated speed and the speed 2 is the subsynchronous speed. Okay, so in order to compute the torque, my first way is to use this approximation using the ratio of the speed. Okay, for the mechanical power is the cube. Okay, for this case is square, and for the mechanical power is cube. This is the first way in order to compute the mechanical torque and the mechanical power. This is my first conclusion, okay? So this is the data. I will have here the stator resistance, the rotor resistance, the leakage inductance for the rotor and for the stator, the rated speed, the number of poles, okay, and besides the frequency of operation. Okay, and besides the frequency of operation. Okay, so let's start the solution. My first question is to compute the generator mechanical torque and power. Okay, so we carry out the analysis of two speeds. Okay, the first one is the operation speed. In this case, is the subsynchronous speed, and the second speed is the rated speed. And then we estimate the new torque and power using the speed ratio. Okay, so let's start with the first part. Okay, in order to compute the new mechanical torque and the new mechanical power, first of all, I will start with the rated values. Okay, so this is the second speed. The second speed, according to the problem, is this operating point. This is my first operating point, and this is my second operating point. Okay, so I will have here 670 RPM. Okay, RPM. So it means a revolution per minute, right? Okay, so I need radians per second. So I will apply the conversion factor, okay? So I will say, for instance, I will say 1 minute, 60 seconds, okay? And one revolution, I will have 2 pi radians. Okay, so this is the conversion factor in order to have radians per second. Okay, so therefore the mechanical power, this is at this speed in radians per second is equal to 70.162, okay, radians per second. What is my objective? My objective is to compute the new mechanical torque and the new mechanical power. Okay, so let's compute the rotor electrical speed. The mechanical quantities, in order to convert to electrical quantities, what I need is the number of pole pairs. Okay, therefore I will say the electrical, this is the rotor electrical speed, is equal to the mechanical speed. In order to convert from mechanical to electrical, I use the number of poles. This is the number of pole pairs, okay? Therefore, according to the problem, the number of poles for this generator is equal to 3. Okay, so I will have this is equal to the mechanical power. We have already computed 17.162 times the number of poles, okay? And the number of poles is equal to 3. Therefore, I will have an electrical quantity, okay? In this case is 210, sorry, 0.48. I will have radians per second. Okay, I will have radians per second. Okay, so this is the operating point. I need to compare with the rated values. Okay, so therefore, in order to make a difference, this is the mechanical speed, but the subscript R means rated value. Okay, so according to the problem, the rated value is this speed, 1170 RPM. Okay, so I will have 1170 RPM. Once again, this is revolution per minute. Okay, therefore I will apply the conversion factor. Yeah, I will get radians per second. Okay, so I will get 1202.52 radians per second. Okay, this is the rated speed. On the other hand, I will have the frequency of operation is 50 Hertz. Therefore, I am able to compute the stator frequency. Okay, the stator frequency by definition is equal to times pi times the frequency of operation. Okay, so it means it's equal to 100 pi. Okay, because the frequency is 50, therefore I will have 314.16 radians per second. Okay, So I have my first speed. I have my first speed. And now I have my second speed. Therefore, I will compute the factor, okay? I will compute the factor. So I will compute the rotor speed is something like the per unit value. In this case, the rated value is equal to the base. Therefore, it's something like the per unit value, okay? So I will have here the ratio, this is the speed ratio in order to estimate the new mechanical torque and the new mechanical power, okay? So I will have, let's call this the per unit because the rated value is equal to the base, okay? So this is the O, this is the actual, and this is the rated value, okay? But in this case, I will have in radians per second, okay? So from the previous calculation, what is my first value is this one. And what is the rated value is this one. Therefore, I will compute the speed ratio. Okay, so I will get 70.162 radians per second over 122.52 radians per second. Therefore, the speed ratio is 0.5727, but in this case, because the rated value is equal to the base, it's possible to say this is the per unit value, right? And this is the factor, for estimating the new power and the new torque at the new speed. This is the factor, okay? So let's start with the mechanical power, okay? The mechanical power is proportional to this speed ratio squared, okay? So I will get, this is the rated mechanical torque times, I will have the mechanical speed. This is the speed ratio, but in this case is equal to the per unit value. So it's proportional to the square, okay, in order to compute the torque. Okay, so let's back. What is the rated mechanical torque? Okay, so let's back to the table. I will have the rated mechanical torque for this turbine is this value, okay, 40,809. Okay, so I will have here 4,000. This is negative, by the way, 4,809. Okay, times the speed ratio. Okay, in this case is proportional to the square. So I will have 0.5727 square. This is my first way in order to compute the mechanical torque. Later on, we will verify. This is the cross-checking using the formula, right? Using the formula. Okay, so let's compute this value. Okay, so the new mechanical torque for question A is equal to negative. So I will have 13,382.4 Newton meters. Okay, this is the rate mechanical torque, and this is the new mechanical torque. Okay, so computing the new torque using the ratio of the speed, I will get this value. Okay, so for the torque is proportional to this speed ratio. What about the mechanical power? The mechanical power is proportional to the Q. Okay, is proportional to the Q. So therefore, let's continue computing the mechanical power in order to finish question A. Okay, so for the mechanical power, once again, starting for the rated value. Okay, that is the reason I have the subscript R. It means rated. Okay, this is equal to, I will have the rated speed, okay, times the rated mechanical torque. So in order to compute the mechanical power at the rated value, I need the rated speed and the rated torque. Okay, so from the previous calculation, we know this value in radians per second is equal to 122. Okay, 52 times the rated torque. The torque is 40,809, sorry. So therefore, the rated mechanical power, okay, is equal to negative. I will have 5,000 times 10 to the power of 3, this is cube, watts. Okay. Okay, so in order to estimate the new power, so I will say the mechanical power using the speed ratio. Okay, the mechanical power is equal to the rated mechanical power, okay, times I will have the speed ratio. In this case, is the per unit value. Okay, so I will copy here the per unit value because I am selecting the rated value equal to the base, but in this case is cube, is proportional. Okay, so therefore the new mechanical power is 5,000 times 10 to the power of 3, this is cube, okay, times the speed ratio. In this case is the per unit value is 0. I will have 5727 cube. Okay, therefore the new mechanical power is 938.94 times 10 cube. Okay, yeah, I will have here watts. Okay, this is the first way. Let's call this the first methodology. Okay, in order to estimate the new mechanical power and the new mechanical torque, because I have two speeds. The first one is the rated speed and the second one is the speed of operation, the operating point. For this problem, the operating point is this speed, okay? And the rated speed comes from the manufacturer data, okay? Comes from the manufacturer data. Okay, this is question A. Okay, this is question A. Let's continue with question B. Yeah, for question B, the problem is asking me to compute the root mean square stator and rotor current, okay? So I will use the exact methodology, okay? So what is the exact methodology? I don't remember if I have the formula here. Okay, so let's back. Okay, this is the approximation. Do you remember this is the methodology too, the simplified method using the stator current. In order to compute the stator current, I will use this formula, right? Yeah, in order to use the exact methodology, okay, the stator current is equal to the stator voltage plus minus. I will have the square root. This is the stator voltage square, okay, minus 4 times the stator resistance, the mechanical torque. This is the rated mechanical torque. This is the synchronous speed, the stator speed. Okay, this is over 3 times the number of poles. Okay, over. I will have 2 times the stator resistance. So we have already derived this equation in the previous class. Okay, so we have already derived this equation in the previous class. So let's substitute in the data. Okay, so I will have the stator voltage. Let's back what is the stator voltage. In this case is this value, right? This is the rated stator line to line voltage is 950. Because this is line to line, I am working per phase. Therefore, I need to divide it by the square root of 3. So I will have 950, okay, over the square root of 3. I will have plus, minus, okay, so I will have 950 over the square root of 3 square minus 4 times. I will have here the stator resistance, okay? And the stator resistance for this problem is this value, okay, 1.552 milli ohms, okay. Okay, so I will have in this case yeah, the value was 1.552 552. 1.552. So I will have 1.552 times 10 to the negative power of 3 in order to have ohms. Okay. What about the rated torque? What about the rated torque? According to this problem, is equal to. So what is the value? So we compute this value. Where is this value? Yeah, is this value, right? Okay, so substituting this value, I will have negative. This is times. Okay, I will have negative 13,384.4 Newton meters. Okay, times the speed. The speed is 2 times the frequency of operation. In this case, is 50 hertz. Therefore, I will have 314.16 radians per second. Okay. Okay, this is the square over. I will have 3 times the number of poles. In this case, the number of poles is equal to 3. Okay. Yeah, I will have over. Okay, so let's clear this part. So this is the stator current. Okay, is equal to 2 times the stator resistance. Okay, so I will have 1.552 times 10 to the negative power of 3. Okay, so because of plus and minus, I will have two currents. Okay, the first one using the plus, I will have the stator current. Yeah, for the first case is equal to negative 849.64 amps. Okay, and for the second case, I will have 35.43 times 10 to the power of 4. Okay, so pay attention to this value. Pay attention to this value. Okay, this value is omitted, okay, because it's bigger. And this value, because of the mode of operation, the stator current is negative. So therefore, I am selecting this value, and this value, and this value is omitted. Okay. Okay, so this is for the stator current. What about the rotor current? Okay, so what about the rotor current? Okay, so let's back to the presentation. Yeah, we'll have here. Yeah, I will have here this figure. Okay. I will have here this figure. Okay, so I will have here the rotor current. Applying Kirchhoff voltage law, we have already derived this equation in the previous class. Okay, so the rotor current, this is phasor. That is the reason I am using the super bar. Okay, I will have J. This is the magnetizing inductance. Applying Kirchhoff voltage law, I will have the stator current. Okay, over. I will have the magnetizing inductance plus I will have the rotor resistance over the slip plus this is the rotor leakage reactance plus I will have the equivalent resistance. Yeah, this equivalent resistance and reactance is the model of the converter, right? Over the slip plus J, the equivalent reactance over the slip. So this is the model of the converter, okay? This is the model of the converter. This part is the model of the converter, okay? So in order to compute the magnetizing inductance, the magnetizing reactance, sorry, is equal to the speed times the magnetizing inductance. Okay, the same for the rotor leakage reactance. Okay, and the same for the stator leakage reactance. I need to multiply the speed times the leakage inductance. Okay, so I will have for this case the leakage inductance and the stator leakage inductance. Okay, so what is the speed? What is the value of this speed? Okay, by definition is 2 times pi times the frequency of operation. Okay, so let's back to the table. Let's clear this. So I will have here the stator leakage inductance. I will have here the rotor leakage inductance. I will have here the magnetizing inductance. Okay, so the frequency of operation in this case is 50 Hertz. Okay, so therefore I am capable to compute these three reactants. Okay, so I have these reactants. I have these reactants. Okay, I have these reactants. We have already computed stator current. This is data, the rotor resistance. Let's back. What is the value of the rotor resistance? So I will have this value. This is the rotor resistance. Okay, so the slip, we have here the rate of the slip. Okay, what is the rate of the slip? Is this value. Okay, this is the rate of the slip, but I need to compute the new slip. Okay, I need to compute the new slip because I have a new operating point. So by definition, the slip is equal to the speed minus, this is the stator minus the rotor speed, okay, over the stator speed. Okay, so let's compute the slip. This value is 314.16. Okay, the rotor speed is 210.48. Okay, over 314.16. Therefore, the slip is equal to 0.33. Okay, what about the equivalent resistance and the equivalent reactance? Okay, so let's back to the problem. According for this mode of operation, this is the equivalent resistance, and this is the equivalent reactance. Okay, and this is the equivalent reactance. Therefore, substituting the whole values. Okay, substituting the whole values in this equation, the rotor current. Okay, so the rotor current is equal to 1092.55. In this case, I will have 163.13 degrees. Okay, this is the rotor current. Okay, this is the rotor current. But I have a second way in order to compute this rotor current. I have a second way. This is my first way. Okay. In order to compute the rotor current using the second methodology, okay, I will use the mechanical torque. This is the definition of the mechanical torque. This is equal to 1 over the stator speed over the number of pole pairs. Okay. 3 times I will have the rotor current. Okay. This is the equivalent resistance plus the rotor resistance, okay, times this is over the slip of times 1 over the slip. This mechanical torque, the unit is Newton meter, okay? So from which isolating the rotor current, this is my second way in order to compute the rotor current, is equal to the square. Isolating, I will have the mechanical torque times I will have the stator speed over the number of poles, okay, over I will have 3 times, this is the equivalent resistance, okay, plus and the rotor resistance over the slip. So this is my second way in order to compute the rotor current. Okay, so substituting the values, I will have the rotor current. Yeah, from the table. Sorry, we have already computed the mechanical torque. For the second speed is 13,308 82.4. Okay, the speed is 314.16. Over the number of poles is 3. Okay, so I will have 3 times. The equivalent resistance, according to the problem, is negative. Let's back to the data. Okay, so I will have this value for the resistance and this value for the reactance. Okay, so I will have 3 times negative. The equivalent resistance is 0. I will have 13, 0. This is 59 plus the rotor resistance. Okay, the rotor resistance is 0. According to the data, 0.001446 over the slip. So we have already computed the slip is 0.33. Okay, so computing this value, I will get the same value. Okay, I will get the same value, 1092.55 amps. Okay, this is question B. Yeah, for question B, the root mean square stator and rotor currents, and for question A, we have already computed the new value for the new speed. So let's continue with question C, the stator and rotor winding losses. Okay, the stator and rotor winding losses. Okay, so for question C, we know the stator winding losses by definition is, because I have 3 cables, is 3 times. I will have the stator current square times the stator resistance. Okay, this is for the stator winding losses. What about the rotor winding losses? I will have here, this is for the rotor. Okay, I will have 3 times the rotor current square. I will have the rotor resistance. Okay, so we have already computed in the previous question the rotor current and the stator current. Okay, so substituting the values, I will have 3 times. Okay, the stator current, we have already computed this value is 849.64 squared times the stator resistance. The stator resistance from the manufacturer is this value. This is the stator winding resistance, and this is the stator winding, the rotor winding resistance. Okay. Okay, so substituting the value, I will have 1.552. Okay, times, because I have milliohms, I will use this conversion factor. Okay, I will use this conversion factor. The same for the rotor. Let's compute this. The stator winding losses is equal to 3.361 times 10 cube. Okay, this is watts. Okay, what about the rotor winding losses? Okay, so I will have 3 times. I have 3 cables too. The rotor current we have already computed in the previous question is 1092.55 square. Okay, times the rotor resistance. Okay, the rotor resistance is 1.446. Yeah, I will use the conversion factor. Okay, in order to have ohms. So therefore, this is equal to 5.168 times, I will have 10 cubed, 10 to the power of 3. This is watts. So that is the way in order to compute the stator and rotor winding losses. Okay. So what is the final question? The previous question, because this is over. So let's continue with the question E. The net power delivered to the grid and the efficiency of the doubly fed induction generation. Okay. Is missing question D, the stator and rotor active power. So let's continue with question D. Okay, let's continue with question D, the stator and rotor active powers. Okay, so for the stator, by definition, the stator active power is equal to 3 times. I will have, in this case, the line to neutral voltage times the line current times the power factor. Okay, times the power factor. Okay, because the power factor is equal to 1, it means I am operating in the subsynchronous mode of operation. It means this angle, for this mode of operation, this angle, I will have here the stator voltage, and this is the stator current. Therefore, the angle is 180 degrees for this mode of operation. Okay, 180 degrees. Therefore, the stator active power is equal to 3 times. This is the line to neutral voltage. I have the line to line voltage. Therefore, I need to divide it by the square root of 3 times the stator current. We have already computed this value is 849.64 amps. And the power factor is the cosine, and this angle is 180 degrees. Okay, this is the angle between the stator voltage and the stator current. Okay, so the stator active power is equal to, I will have 1398 times, I will have 10 cube. This is the power of 3 watts. Okay, so for the rotor power is equal to 3 times, I will have the rotor current square, but in this case I am using the equivalent resistance, okay, because I am modeling the converter, right? I am modeling the converter. So in the previous calculation, we used the rotor resistance in order to compute the rotor winding losses. In this case, I need to compute the rotor active power. For that, I will use the equivalent resistance because I am modeling the converter. Okay, so this is equal to 3 times, I will have 1092.55 square, okay, times, I will have negative, the equivalent resistance for this mode of operation is, the equivalent resistance for this mode of operation is this value, right? Is this value. So I will have negative 0.13055 ohms. Therefore, the rotor active power is negative 467.64 times 10 cube. This is 10 to the power of 3 watts. But the problem is asking me to compute the net power delivered to the grid, okay, for this mode of operation. So therefore, in order to compute the net power delivered to the grid, okay, so for this mode of operation, do you remember, this is the grid active power is equal to the stator, this is the magnitude, okay, plus the rotor active power, okay, plus the rotor active power. Therefore, in order to compute the net power delivered to the grid, I will have this power is 1,300, okay, 98 times 10 cube, okay, minus, I will have 467.64 times 10 cube. This is the magnitude, this is positive, okay? So therefore, this is the net power delivery to the grid. This is equal to 930.4 times 10 cube, okay, watts, because of the mode of operation, okay, because of the mode of operation. In this case, I will have a subsynchronous mode of operation. So that is the way in order to compute the grid power, okay, in order to compute the grid power. On the other hand, the difference between the mechanical power, okay, the difference between the mechanical power and the grid power, okay, is the losses on the stator and rotor winding. So once again, the difference between this mechanical power and the grid power is the losses on the stator and rotor windings. Okay, so let's verify this value. So I will have, this is negative, this is 900, this is 38.94 times 10 cube, this is the mechanical power, minus the grid power, in this case is this value, 930.4 times 10 cube, this is to the power of 3, this is equal to 8.539 times 10 cube watts, okay? And we know this difference, okay, so the difference between the mechanical power and the grid power is the losses on the stator and rotor windings, okay? So this is equal to the stator and rotor windings. In this case, I will have the stator winding losses plus the rotor winding losses, okay, plus the rotor winding loss. So the problem is asking me to compute the efficiency of the doubly fed induction generation, neglecting rotational and core losses, okay? So therefore the efficiency, by definition, is equal to, in this case, is the grid power, this is the output power, over the mechanical power. This is the input power. The output over the input is the efficiency, okay? So from the previous calculation, I will have this power is 934 over the mechanical power. 900, I will have 38.94. In other words, this is the output power and this is the input power. Okay, so therefore the efficiency is 99. I will have 0.9%. This is in percentage, okay? This is in percentage. So the last question, let's back to the problem. Yeah, the last question is to compute the fundamental grid current, okay? So let's compute this current is for the last question, question F, okay? So we know the grid power by definition is equal to 3 times the grid voltage times the grid current. Okay, so isolating this current, I will have the grid current is equal to the grid active power over 3 times the grid voltage. Okay, so substituting the values, I have 930.4 times 10 cube. This is the grid power. We have already computed this value. Okay, over 3 times. What is this value? The grid voltage is the rated value, but in this case I am using the line to neutral voltage, okay? So the line to line voltage is given by the manufacturer, okay? But I need the line to neutral voltage. That is the reason is over the square root of 3, okay? Therefore, the grid current, okay, is equal to 565.44 amps. 44 amps. Okay. So in the beginning, I say I have two methodologies in order to compute the mechanical power, the mechanical torque, and the mechanical power. So do you remember my first methodology is using the equation is proportional to the square, right? So we have already used this formula, the mechanical torque for the new speed is equal to the rated mechanical torque times this speed ratio. So my first way, in order to compute the new mechanical torque is using the speed ratio. Okay, so we compute this value, and this value was 0.4 Newton meter. Okay, this is the mechanical torque. My first way, in order to compute the mechanical power, in this case is proportional to the cube. Okay, is proportional to the cube. So in the previous calculation, we know this value. Is equal to, this is the rated mechanical power times the speed ratio. Okay, what is the reason I call the per unit value? Because the base is equal to the rated value. In this case, it's the same. Okay, Therefore, I will have the mechanical. This is the speed ratio. This is Q. So we compute this value, and this value was 938.94 times 10 to the power of 3. This is Q. Okay, so this is my first way in order to compute the mechanical power and the mechanical torque. So let's verify with my second methodology. Okay, for my second methodology, we have the formula. So in the previous class, we derived this formula, and the mechanical torque is equal to 1 over the speed over the number of pole pairs times, I will have 3 times the rotor current square, okay, times the equivalent resistance plus the rotor resistance over the slip. Okay, so substituting these values, I will have the speed is 314.16. The number of poles is equal to 3. The rotor current, we have already computed this value, is 1092.55 square. Okay, the equivalent resistance is data from the problem, so I will have negative. This is 0.13095. The rotor resistance comes from the manufacturer, is 0.001446, and we have already computed the slip for this for the subsynchronous mode of operation, and this value was 0.33. Okay, so substituting these values, we can verify, yeah, I will get the same value. Yeah, I will call this cross check. The validation is called the cross check. Okay, so it means this value is verified. So I will get the same value, 13,382.4 Newton meters. I will get the same value. This is called cross check. So this value is verified. So I will have a second way. In order to compute the mechanical power. Okay, so we have already derived this equation in the previous class. The mechanical power by definition is equal to 3 times the rotor current square times, I will have the equivalent resistance plus the rotor resistance times 1 minus the slip over the slip. Okay, so once again, substituting these values, in this case, I will have the rotor current 1092.55, okay, square. The equivalent resistance is equal to negative 0.13095, okay. The rotor resistance is this value, 0.00, I will have 1446. And what about the slip? The slip is 0.33. So I will have 0.33 in the numerator. I will have 0.033 in the denominator. Okay. Therefore, once again, substituting these values, I will get the mechanical power is equal to negative 938.9 times 10 cubed. In this case is what? So once again, this value is verified. Let's call this the approximation, and let's call this the exact methodology. Okay, so I have 2 ways in order to compute the mechanical power and the mechanical torque. So I have already cross-check. Okay, I will get the same value. I will call this the second methodology. Okay, and this is my first methodology. Approximation is proportional to the speed ratio square, and this is proportional to the speed ratio Q. Okay. Okay, guys, so continue. Let's continue with the next part. And the next part is the last part. Okay, and the last part is 64. This is the torque slip characteristic. Okay, so in the previous part, yeah, in the previous part we are working in the unity power factor operation. Okay, and besides, we have already derived the steady state equivalent circuit with the rotor side converter. Okay, yeah, for the last part, what is missing is to analyze the torque slip characteristic. And in this case, I am changing the mode of operation. I am not operating at unity power factor. In this case, I am operating either leading or lagging power factor operation. Okay, so let's start with the first part, the torque slip characteristic. Okay, and later on we continue with the leading and lagging power factor operation. Okay, so in order to find the torque slip characteristic of the double effect induction generation, okay, so we need to add the total rotor circuit resistance. Okay, so this is the rotor resistance. I need to sum the equivalent resistance. Okay, so that is the way in order to find the torque slip characteristic. This is for the resistance, and besides I need to have the total reactance. Okay, so I will have the rotor leakage reactance. I need to add once again plus the equivalent reactance. So that is the way in order to analyze the torque slip characteristic. Okay, so in this case I will have the mechanical torque. I will have here the slip. Okay, so this figure shows a set of typical torque slip curves of the double effect induction generator operating. I will have the subsynchronous, supersynchronous, and subsynchronous mode of operation. Okay, so I will have a lot of operating points, taking into account the slip. So in this case is positive, in this case is negative. Okay, in this case is negative. So in a maximum power point tracking, maximum power point tracking control, the mechanical torque is proportional. The mechanical torque is proportional to the rotor speed square. Okay, so this I will plot in curve 4. Okay, I will plot in the curve 4. Okay, so pay attention to this part. I will get 2 points of operation. This is the intersection point B, and this is the intersection point A. Okay, so let's make a look in the operating point, in the intersection point A. Okay, so I will have curve 4 is intersect with curve 1. Okay, so I will have the curve 4 is this one, is intersecting with the curve 1. So I will have here this. This is the curve 1. Okay, this is the intersection point. So where curve 4 intersects with curve 1, I will have the generator operates in super mode of operation because the slip is negative. Okay, because this slip is negative 0.005, this is a super synchronous mode of operation. Okay, in this point, I will have a super synchronous mode of operation in this operating point between when the curve 4 intersects the curve 1. I will get this intersection point, and the slip for this point is negative. Therefore, I will have a super synchronous mode of operation. Okay. What about the point B? So once again, I am analyzing the curve 4. Okay, it intersects. In this case, curve 4 intersects with curve 2. So this is my curve 2. and this is the intersection point. So pay attention, what is the sleep? The sleep is 0.05. Okay, so the machine operates in subsynchronous mode of operation. In this case, the machine is operating in subsynchronous mode of operation because the sleep is positive. Okay, because the sleep is positive. So in this case, between this value and this value, okay, the sleep is positive or negative. It means the double-fed induction generator is always in generator mode. Okay, between this band of operation, the sleep is positive or negative. So therefore, my main conclusion, the double-fed induction generator, okay, is always in generator mode. It means it's not motor, okay, is always in generating mode and delivers its mechanical power to the grid. Okay, so in this band of operation, the generator delivers mechanical power to the grid. Okay, mechanical power to the grid. So on the other hand, for comparison purposes, I will have the core 5. Okay, so let's analyze this core 5. Yeah, I will have here the maximum torque. Okay, so in this case, in order to plot the core 5, I am assuming the equivalent resistance is equal to the equivalent reactance, and this is equal to 0. It means the rotor is short circuit, because do you remember when I have the equivalent resistance and reactance, it means I am modeling the converter, okay? So in this case, if the equivalent resistance and the equivalent reactance is equal to 0, means the rotor is short circuit, okay? The rotor is short circuit. Therefore, I will get the torque slip characteristic of the double-fed induction machine, in this case, if the power factor is equal to 1. So pay attention to this part. This is the equivalent reactance. And down, let's plot the equivalent resistance. Okay, so for the subsynchronous, for the supersynchronous mode of operation, these values are negative. Okay, and for the other mode of operation are positive. Okay, so I will have the supersynchronous mode of operation. This is the intersection point A, and the subsynchronous mode of operation is the point B, because I will have here the sleep is positive and this is negative. Okay, so if I change the speed, I am able to plot the equivalent resistance and the equivalent reactance. Okay, for these 2 points of operation, for B and for A, I will have these values. Okay, yeah, I will get these values. Okay, so this is the torque slip characteristic of the double-fed induction generator with the power factor is equal to 1. Okay, so pay attention in the core 5. I need to compute the maximum torque. So do you remember for the calculus, I think, course, in order to find a maximum and minimum value, what should I do? What shall I do? Okay, so Mr. Salazar, my objective is to compute the maximum, either the maximum or the minimum value. What shall I do if I have the equation of the mechanical torque?
We can derivate and equal to 0 the equation. I don't.
That is right. I need to take the derivative, okay? And this derivative is equal to 0. That is the way in order to compute a maximum, either a maximum or minimum, okay? So in order to find the maximum torque of the double-fed induction generation, a simplified steady-state equivalent circuit can be used, okay? So pay attention to this part. This is the reactance, and the reactance is moving to the left side. So I will get this equivalent circuit, okay? So pay attention, the only difference is the moving of this reactance to the left side. So finally, I will get this equivalent circuit. What happened in this equivalent circuit? The magnetizing branch is moved to the left side of the stator circuit. So I will have this equivalent circuit. Yeah, I will compute the maximum torque. Okay, so for this case, the magnetizing inductance is much higher than the resistance and the inductance on the stator side. Okay, So I will use this approximation. And because of the stator resistance and the stator inductance are smaller if I compare with the magnetizing inductance. Okay, this equivalent circuit not generate large errors in the calculation. Okay, so therefore I will use this equivalent circuit. The only difference, once again, the magnetizing branch is moved to the left of the stator circuit. Okay, so I will have here the magnetizing inductance. Okay, so now in order to compute the electromagnetic torque of the generator, I will say by definition the electromagnetic torque, okay, is equal to the air gap power over the stator speed over the number of poles. Okay, over the number of poles. Okay, so therefore this is equal to in order to compute the air gap power. Okay, so do you remember from the induction machine course, by definition this is equal to 3 times, okay, the rotor current square. I will have the rotor current plus the equivalent resistance, the rotor resistance plus the equivalent resistance over the slip. Okay, over the slip. So let's call this equation number 1, and this is equation number 2. Substituting equation number 1 into equation number 2, sorry, into equation number 1, I will get the following formula. So I will have 1 over, I will have the stator speed over the number of poles, okay, times, I will have the air gap power, this is equal to 3 times the rotor current, okay, times the rotor resistance plus the equivalent resistance. When I see this equivalent resistance, either resistance or inductance, means I am modeling the converter, okay? I am modeling the converter over the slip, okay, over the slip. So I will apply Kirchhoff voltage law. I will apply Kirchhoff voltage law in this loop. Okay, I will apply Kirchhoff voltage law in this loop. Okay. This is the final formula, okay? So I will get 1 over, this is the stator speed over the number of poles, okay, 3 times. I will have the rotor current square times the rotor resistance plus the equivalent resistance over the slip, okay, over the slip. Okay, so applying Kirchhoff voltage law in this loop, I will compute the rotor resistance, the rotor current, sorry. Okay, so I will have this voltage, applying Kirchhoff voltage law, this voltage is in this branch, okay, plus the voltage drop across this equivalent impedance times the current, okay, is equal, plus this voltage is equal to 0. So I need to isolate the current from this circuit, from this equivalent circuit. So first of all, applying Kirchhoff voltage law and later on isolating the rotor current, okay, substituting in this equation. So I am substituting the current from this, I am substituting in this equation, I will get the electromagnetic torque of the generator can be expressed as the following equation, okay? So I will have 1 over the stator speed over the number of poles, okay? So I will have 3 times, substituting the rotor current, I will get the stator voltage square, okay? I will have, this is the stator resistance, this is the stator resistance, plus this resistance and plus this resistance. Okay, so I will have a stator resistance plus the rotor resistance over the slip plus the equivalent resistance over the slip. Okay, I will have here a square. What is the reason a square? Because this is a square. Okay, this is for the resistance. What about the reactance? So for the reactance, taking out this reactance plus this reactance plus this reactance, okay? So I will get plus, this is the stator leakage reactance plus the rotor leakage reactance plus the equivalent reactance over the slip. Once again, this is over the slip. Once again, a square. Okay, once again, a square. Okay, so this is the core. What is missing? What is missing is this term. So times, this is times, I will copy up, but it's times. This is the rotor resistance plus the equivalent resistance over the slip. So taking this approximation, this is the simplified double effect induction generation steady state equivalent circuit only for computing the maximum torque. Only for computing the maximum torque. So this is the torque, okay? So I take the derivative in order to compute the maximum torque and the maximum slip, okay? So this is the equation of the mechanical torque, the electromagnetic torque, okay? So I will take the derivative. So this taking the derivative of this equation with respect to the slip, and this is equal to 0, I will get the maximum slip. Okay, I will get the maximum slip. So later on, solving this equation equal to 0, I will isolate the slip, and this is the maximum slip. Okay, so pay attention, this is plus minus. It means I will get 2 slip. Okay, substituting this slip. So once again, substituting the maximum slip. So I will substitute here, this is the maximum slip. I will have the maximum slip. Substituting the maximum slip here, here, and here, I will get the maximum torque. And this is the final formula in order to compute the maximal torque. And this maximal electromagnetic torque is a function of the reactances and the resistance, and besides the number of pole pairs, the stator frequency, and the stator voltage. Okay, so this is the equation. We have already derived the equation. In order to find the maximum and the maximum torque and maximum slip, I need to take the derivative and equal to 0. Solving the equation, I will get the maximum speed. Later on, substituting the maximum speed in this equation, I will get the maximum torque. Yeah, is that clear, Mr. Mejia?
Yes, doctor, it's clear.
Okay. So we will continue. In order to make clear these formulas, we will continue with the next problem. Okay. And the next problem is problem 5. Okay, so Mrs. Sola, are you there?
Yes, doctor.
Yeah, could you please read over the problem 5?
Yes, of course. 1 megawatts, 575 volts, 60 hertz, 160 revolution per minute. Double feed induction generator is used in a variable speed wind energy conversion system. The parameters of generator are given in table. The generator operates with an MPPT scheme and its stator power factor is unity. Assuming that the double feed induction generator operates at supersynchronous speed of 2160 revolutions per minute, determine the following. Letter A, the generator mechanical torque and power. Letter B, the RMS stator current, the RMS magnetizing voltage and current, and the letter D, the RMS rotor current and voltage. Letter E, the equivalent resistance and reactance for the rotor side converter. The letter F, the maximum torque and the corresponding slip.
Thank you. So one question is coming out. So pay attention to this part. This is the rated sleep. And besides, the double effect induction machine is operating at super synchronous speed. You can see it's the same value. Okay, so my question is, what is the speed ratio? What is the speed ratio, Mr. Rocha? Mr. Rocha, are you there?
Yes, doctor.
What is the speed ratio?
The speed ratio.
So do you remember we have two methodologies in order to compute the mechanical torque and the mechanical power, okay? In the first case is proportional to the speed ratio square. In the second case is proportional to the speed ratio Q. Okay? This is, let's say, an approximation. This is an approximation. So we have two ways in order to compute the mechanical torque and the mechanical power. The first one is using this approximation, okay? And the second one is using the formulas. So later on, I will cross-check, okay? So do you remember in the previous problem, we had two speeds. The first one was the rated speed, and the second one was the supersynchronous speed. And we compute the speed ratio, okay? And we get this value, and we call this the per unit value. In this case, because of this value is equal to this value, what is the speed ratio? Anyone? Any clue? Any clue? Guys, are you there? What is the speed? Is 1, right? Thank you, Mr. Mejia. Is 1, because the ratio of the second speed is 2160 over 160. It means the speed ratio is 1. Okay? Anyway, let's compute using the two methodology. Okay, so for the data from the problem, I need the frequency of operation. In this case, pay attention, is 60 Hertz. This is the frequency of the system. And later on, I will have the rated mechanical speed. The rated mechanical speed, I will get what is the speed, is this value. Okay, what is the rated sleep, is this value. What is the number of pole pairs, I will have 2. Okay, this is the rated mechanical power, mechanical torque. Okay, with the torque, I am able to compute the power, right? This is the stator winding resistance, the rotor winding resistance for this generator. This is the stator leakage inductance, the rotor leakage inductance. Okay, so this is the data in order to compute the electromechanical torque and the mechanical power. So let's continue with the first part, the generator mechanical torque and power. From the previous problem, we established the methodology. Okay, so I will follow the same methodology. Okay, so I will start question A. I will compute the mechanical torque. So starting from the rotor mechanical speed. Okay, according to the problem, for this subsynchronous mode of operation, okay, for this supersynchronous mode of operation is 2160. This is my second speed. Okay, this is my second speed. I am talking about this speed. This is the rated value. Okay, later on I will talk about the second speed. This is my first speed. So this is a revolution per minute. Okay, so taking out, multiplying by the conversion factor, I will have 2 times pi over 60. Okay, so I will get 226.19. In this case is radians per second. Okay, I am using, this is the conversion factor. Okay, later on, in order to convert mechanical quantities to electrical quantities, I will use the number of poles, right? So therefore, I am computing the rotor electrical speed. This is equal to the mechanical speed times the number of poles. Okay, So this is equal to 100, following the same methodology from the previous problem. Okay, I will have this times the number of pole pairs. This is equal to. Therefore, the rotor electrical speed is 400. I will have 92.39. In this case, is radians per second. Okay, radians per second. Okay, this is for the speed 2. This is the supersynchronous mode of operation. Okay, so I need to compare with the rated speed. Okay, so the rated rotor mechanical speed, this is my second speed. That is the reason I am using a double subscript. The first one means mechanical, and the second subscript means the rated value. Okay, so for the rated value, let's back to the table. This is the rotor speed. This is my second speed, is 2160 RPM. Okay, so I will have 160 RPM. Once again, using this is the conversion factor. Okay, I will get the same value, of course, 226.19 radians per second. Okay, I am using the conversion factor. What about the stator frequency? According to this problem, the frequency of operation is 60 Hertz. Okay, so the stator frequency by definition is 2 times pi times the stator frequency. The stator speed is equal to, substituting, I will have 60 Hertz. It means 376.99 radians per second. In a similar way, is equal to 120 pi radians per second. Okay, this is the stator frequency. Okay, so now let's compute the speed ratio. Because the base is equal to the rate value, okay, is the same. This value is equal to the per unit value, in other words. Okay, so therefore I will have the per unit value. This is the speed ratio. Okay, is equal to the speed. This is my first speed. Yeah, I will compare with the rated speed. Okay, but in this case we have the same values. Okay, so 226.19 over 226.19. Therefore, the speed ratio in this case is the per unit value is 1 per unit. Okay, is 1 per unit. So this is the factor for estimating the new torque at the speed, at the new speed, the mechanical and at the new speed. This is the factor. In this case is 1. Okay, so the generator mechanical torque at 1 per unit rotor speed. So let's estimate the mechanical torque using the speed ratio. Okay, let's estimate the mechanical torque. Yeah, I will call this the first methodology. Okay, so let's compute the new torque using the ratio of the speed. Okay, so this is the rated mechanical speed times the speed ratio. In this case, is equal to the per unit value. Is proportional to the square. Okay, is proportional to the square. So the electromechanical torque, let's back to the rate value. What is the rate value? In this case is this value, right? 4,421 kilonewton meters. So I will have 4,000 in Newton meters, 4,421 Newton meters times the speed ratio. In this case is equal to the per unit value. So 1 square. That is the way in order to estimate the electromechanical torque. Okay, so is equal to 4,421 Newton meters. Okay, this is the mechanical torque. Okay, so now in order to estimate the mechanical power for this new speed, I will start computing the mechanical power, the rated mechanical power. Okay, so the rated mechanical power, okay, is equal to the rated mechanical speed times the rated mechanical torque. Therefore, substituting the values in radians per second is 226.19 radians per second times the rated electromechanical torque. So it's equal to 421 Newton meters. Therefore, the rated mechanical power is equal to negative 1000 times 10 cubed. I will have watts. Okay, this is the rated mechanical power. So now let's estimate the generator mechanical power using the speed ratio. Okay, so computing the new torque using the ratio of the speed, I will get in this case is proportional to the cube. Okay, so I will say the new mechanical power using as the reference the rated mechanical power times the speed ratio. In this case is equal to the per unit value, but is proportional to the cube. Okay, is proportional to the cube. Therefore, I will have 1000, okay, times 10 cube. This is the power of 3 times 1 cube, because it's proportional to the speed ratio. In this case, the speed ratio is equal to the per unit value. Therefore, I will get the same value, 1000 times 10 cube watts. This is question 8. Okay, yeah, I will get the same values because the rated value is equal to the new speed. The rated speed is equal to the new speed. That is the reason I get the same values. And this is the first methodology. Okay, this is the first methodology, and this methodology is only an approximation. Okay, is only an approximation. So let's continue with question B. And the question B is about the root mean square stator core. Okay, so once again I will use the exact formula. Okay, the exact methodology. So the stator current, okay, is equal to the stator voltage plus minus the square root. I will have here the stator voltage square minus 4 times, this is the stator resistance, okay, the electromagnetic torque for this new speed. This is the stator speed over 3 times the number of pole pairs, okay, over, I will have 2 times the stator resistance. Okay, so once again, I am working per phase, okay, and from the table, I will have the line to line voltage, okay. So in order to have the line to neutral voltage, I need to divide it by the square root of 3. Okay, I need to divide it by the square root of 3. In this case, the rate mechanical torque is the same. Okay, the stator resistance, what is the stator resistance? Is this value. Okay, what else? And the number of poles is equal to. Okay, so I will get. Okay, so I will get. First of all, the stator voltage, in this case is the line to neutral voltage, is equal to 575. This is the line to neutral, therefore I need to divide it by the square root of 3. Okay, in this case the electromagnetic torque for this new speed is equal to the rated electromagnetic torque. Okay, it means 4421 Newton meter. Okay, the stator speed, the frequency of operation is 60 Hertz, therefore I will have 2 times pi times 60. Okay, and this is equal to 376.99 radians per second. Okay, so the stator resistance is equal to 3.654 milliohms. Okay, so times, I will use the conversion factor in order to have ohms. Okay, and the number of poles is equal to. Okay, so let's compute the current using plus and negative because I am solving a quadratic equation. Okay, so therefore the first current is equal to, so I will get 2 current, and the first current is 829 point, I will have 18 amperes. Okay, and the second current is 91.68 91.682 times I will have 10 cube amps. Okay, so because of the supersynchronous mode of operation, I will get this current. And this current is omitted. Okay, and this current is omitted. So this is question B, the stator current. Okay, so let's back to the problem. What about question C? Question C is the root mean square magnetizing voltage and current. Okay, the root mean square magnetizing voltage and current. So I will use the equivalent circuit. Okay, and from the previous class, we have already demonstrated the magnetizing voltage, the magnetizing branch voltage is equal to the stator voltage applying Kirchhoff voltage law minus this is the stator current, okay, times the stator resistance plus the stator speed times the stator leakage inductance. Okay, so the magnetizing voltage is equal to, this is per phase, right? So I will have the line to neutral voltage is 557 over the square root of 3. And besides, this is the reference, okay? That is the reason I have 0 degrees. Well, we have already computed in the previous question, the stator current is 829.18. Because I am working with a subsynchronous mode of operation, it means this is the stator voltage. And this is the stator current, so I will have this angle is 180 degrees. Okay, times the stator resistance is equal to 3.654. I am using the conversion factor 10 to the negative power of 3 in order to have ohms. Plus, I will copy down, so I will have plus J. The speed is 2 times pi times the frequency of operation. Okay, so I will have 120 times pi times the stator leakage inductance. So once again, I am using the conversion factor, so I will have 0.1304. Using the conversion factor, I will use 10 to the negative power of 3. Okay, therefore, this magnetizing voltage is equal to, this magnetizing voltage is equal to 337, okay, 0.48, okay, I will have 6.94 degrees. Okay, this is the root mean square value, this is the voltage. Okay, in order to compute the magnetizing current, okay, so I will apply once again Kirchhoff voltage law. We have already derived this equation in the previous class, is equal to the magnetizing voltage over, I will have J, this is the speed, okay, times the magnetizing inductance. Okay, so this is equal to, so I will have 337.48 with 6.94 degrees, okay, over, I will have J, this is the speed, is 200 pi, is 2 times pi times the frequency of operation, it means 120 pi. And the magnetizing inductance according to the problem, 0.00412. Okay, therefore the magnetizing current is equal to 270.28 with negative 83.1 degrees. Okay, this is amps. Okay, this is the root mean square value. Okay, so let's continue. I want to compute, if I know the stator current and the magnetizing current applying Kirchhoff current law, let's compute the rotor current applying Kirchhoff current law. We have already demonstrated from the previous class too. So I will have the stator current minus the magnetizing current. So we have already computed the stator current and the magnetizing current. Therefore, This is equal to 829. 829.18. Okay, yeah, you will get here 180 degrees minus the magnetizing current 217.28 with 83.1 degrees. This is the rotor current. The superbar means phasor, no? The superbar means phasor. Therefore, the rotor current is equal to 882.19. Okay, and the angle is 165.85 degrees. This is amps, root mean square value. Okay, so with the rotor current, let's back to the question. I need to compute the rotor voltage. Okay, and then I will compute the equivalent resistance. In order to compute the equivalent resistance, what I need is the rotor current and the rotor voltage. Okay, so question E is related to question D, in other words. Okay, so let's compute the rotor voltage from the previous class. We have already demonstrated this equation, the slip times the magnetizing voltage minus I will have the rotor current. This is the rotor resistance plus J times the slip. This is the stator speed times the rotor leakage inductance. Okay, times the rotor leakage inductance. Therefore, let's compute the slip. Okay, so for the slip, I will get the stator speed minus the rotor speed over the stator speed. This is the definition of the slip. Okay, so I will have 376.99. This is the stator speed minus the rotor speed, 452.39 over. I will have 376.99. So therefore, this is equal to 0.2. In this case, because the subsynchronous mode of operation, this speed is equal to this speed, the slip is the same, only for this situation, okay? I will get the same slip. Okay, I will get the same slip. Okay, so therefore, let's compute the rotor voltage, okay? The rotor voltage is equal to negative 0.2 times the magnetizing voltage is 337.48, okay, with 6.94 degrees, okay, minus the rotor current, I will have 882 with 165.88 degrees times, I need to multiply by the rotor resistance according to the manufacturer. Okay, this rotor resistance is equal to 0.003569 plus J. Okay, I will have the slip negative 0.2. I will have the stator speed is 120 pi times the rotor leakage inductance. Okay, so let's back. The rotor leakage inductance is this value. Yeah, I will use the conversion factor in order to have Henrys. Okay, so I will have 0.001198 using the conversion factor. Okay, so let's use brackets. Okay, so therefore the rotor voltage. Okay, so the rotor voltage is equal to, in this case, is equal to 69.97, and the angle is negative 165.83 degrees. Okay, 83 degrees. So in order to compute the equivalent impedance for the rotor side converter, okay, I will use the relation between, by definition, is equal to the rotor voltage over the rotor current. Okay, the rotor voltage is 67.97 and the angle is 165.83 degrees. Over, I will have the current, and the current we have already computed this value is 882.19 with 165.85 degrees. Okay, 165.85 degrees. Therefore, the equivalent, this equivalent resistance, so splitting up in the real and imaginary part, I will have 0.06782 plus J, 0.03656 ohms. And this is the equivalent resistance. And this value is the equivalent reactance. Okay, and this value is the equivalent reactance. Okay, so this question E, I think, the equivalent resistance for the stator, for the rotor side converter. If I am talking about the equivalent resistance and reactance, once again, is the model of the converter. Okay, the last question is to compute the maximum torque and the corresponding slip. Okay, the maximum torque and the corresponding slip. So we have already derived the equations. Okay, so we have already derived the equations. Okay, and the equations, the slip at which the maximum torque occurs can be computed for the previous demonstration. So this is the maximum slip. We have already derived this equation is equal to plus minus. So I will get the rotor resistance plus the equivalent resistance square plus the equivalent reactance square. So we have already derived this equation over, I will have the stator resistance square plus I will have the stator leakage reactance plus the rotor leakage reactance square. Okay, so this data come from the manufacturer, right? This data come from the manufacturer. And the equivalent resistance and reactance, we have already computed these values here. Okay? Therefore, I will have two possibilities, okay? Using the plus and minus. So for the first case, I will get negative 0.84. For the second case, sorry, is negative 84.97. And for the first case, I will get plus 0.8497. Due to the mode of operation, I am selecting this value, and this value is omitted. Okay, so what is the reason the plus maximum slip is omitted? Because of the supersynchronous mode of operation. Do you remember from the slip torque characteristic for the supersynchronous mode of operation, the slip was negative, okay? That is the reason I am omitted this value. Okay, so finally, let's compute the maximum torque. Okay, so in order to compute the maximum torque, so we have already derived this equation, okay? We have already derived this equation. Okay, so once again, let's analyze what is the stator voltage. The stator voltage is the line to neutral voltage, okay? It means what is the voltage for this case using this equation, okay? I want to use this equation in order to compute the maximum electromagnetic torque. Okay, so let's analyze the data. This is the slip, okay? Okay, so for this case, the stator voltage is equal to 575 over the square root of 3. Okay, this is the equivalent resistance, this is the equivalent reactance. Okay, the number of poles is equal to. And what else? What else? The stator resistance is data from the manufacturer. The rotor resistance is data from the manufacturer. The stator leakage reactance, the rotor leakage reactance is data from the manufacturer. Okay, so therefore I have the old parameters. Okay, so substituting these values, I will get the maximum torque, and the maximum torque is equal to negative 16,214 Newton meters. Okay, Newton meters. Okay, this is the last question. Okay, guys, so that is it for today. Okay, and let's talk about the grading system for the first quarter. Okay, due to the time, I don't know what is the reason I have forgotten to send you the timetable, right? Okay, anyway, no problem, because it's my fault. Okay, so let's analyze December, and the next class is the 8th, the 8th, the next year. Yeah, because from 24 to the 1st of January, we have holidays, right? Okay, so the next class is January. Okay, so for the first quarter, we have class. Let's say the exam could be this date. And for this date, we have not the project, let's call this the lab session. The project is for the second quarter. Okay, so yeah, from 12 to 14, we have class. Normal class, okay? For, I don't know, 16 to 18, we have the exam. Because I need to recover 2 classes, right? The same for January 8 and the same for January 15. So we have class in this schedule. And this schedule, we have for January 8, we have the exam. And for January 15, we have the lab session. What is the lab session? Okay, so I will send you a book. You need to reproduce the simulations. Okay, you need to reproduce the simulations. This is the lab session. I think no time for two lab sessions. It's probably you have only one lab session. Okay, let me think today. So I will upload the lab session today in Teams. Okay, so you can check in the afternoon, in the evening. Sorry, you can check the lab session. Okay, and for January 18, we have the exam. Is that clear? The grading system. No time for other tasks. So the project is for the second quarter, of course. Okay, so we need to split up the lab session. The lab session, I will have 2 components. The first component is the presentation. And the second component is the report. Okay, so this is 30%, and this is 40%. Do we have homework, Mr. Mejia? Do we have homework?
No, doctor. Don't have any.
Okay, so due to the time and taking into account is my mistake. Okay, the grading system for the first quarter is this one. The exam is 40%, and the lab session is split up in 2 components. The first one is the presentation, and the second one is the report. So I will have 100%. Okay, I will have 100%. For the second quarter, I will have the project and the next lab session. And besides, we have homeworks too. Okay. Okay, guys, no problem. It's my mistake. So that is the reason we have only 2 tasks for this first quarter. Is that clear, guys?